So we are now going to a different part of this chapter where we will be speaking about objects hitting each other, and we'll be talking about maybe a 1D collision or maybe a 2D collision, and 2D and 3D will almost be of the same kind, so we are not going to make a distinction over there, but 1D is far simpler than 2D or 3D, so we will definitely make a distinction there. So we need to first of all define what is a 1D collision, what is a 2D collision. And as you will see when I'm explaining the mechanism of 1D collision, that we cannot now deal with point objects. We will have to deal with large objects. So keep in mind that when we are dealing with collisions, we are no longer dealing with point objects. So objects have a finite size. They are also deformable. So we are not talking about rigid bodies, because you can't have rigid bodies hitting each other and then bouncing off in a certain way. At least one of the objects has to be deformable. So objects have a finite size and they are deformable. So this is one. Now when these objects they hit each other, when these large objects they hit each other, they will be first of all in contact at a certain point on their surfaces. So maybe you have got a first object that is here somewhere, and it goes and hits another object that is placed there somewhere. So when this red object goes and hits this reddish brown object here, maybe this point on the surface, this one, these 2 points will come in contact initially, and at this place what we can do is we can draw a common normal. Wherever the contact is, so you can take this figure, paste it and show how the contact will be. So what will probably happen is, as the red object keeps on moving, there, right? So at this point the object on the left and the object on the right are going to be in contact, and at that contact point I can think of a small surface of contact like that green surface, and as soon as I think of a surface of contact, I should be able to draw a common normal. So there will always be a common normal at the point of contact, and that common normal will be called the line of impact. So keep in mind that this guy is the line of impact. That's the line along which impact happens. So line of impact. This is the common normal at the point of contact. And these two objects may have their centers of masses somewhere. So this entire object may have the center of mass maybe somewhere here, close to that orange line, but not exactly on that orange line. And the red object may have the center of mass somewhere pretty far away from the orange line, somewhere there. So the centers of masses of these objects may or may not lie on the line of impact. Now if these centers of masses actually lie on the line of impact, then we have something called a central collision or a central impact. So we have got a central impact. If the center of mass of both the bodies lie on the line of impact. So that's how we define central impact. So maybe an example for spherical balls will be good. So you have two spherical balls. One is maybe this red ball and the other is perhaps a green ball somewhere here, and these two balls are hitting each other, maybe of different sizes, So let me just change the size, like this. And then you will be seeing that the line of impact will be this orange line, and the center of masses of these objects, for the red one it is present on that orange line, the green one also is present on that orange line somewhere. So then this impact will be called a central impact. Now you should see that in this impact I have not drawn the velocity vectors. So the balls may be moving in some other directions, it doesn't matter. But what we are going to have is a central impact. Now what happens during the central impact is the force exerted by the red ball on the green one will go through the center of green one, center of mass of the green one, and the force exerted by the green one on the red one will go through the center of mass of the red one. So there will be a force on the green ball, that is this green arrow here, and there will be a force on the red one, which is this red arrow there. The forces will be equal in magnitude and opposite in direction, and because these forces are going to go through the centers of masses of these objects, they are not going to cause any torque on any of these objects. So the objects' angular velocities are not going to change. If they were rotating before collision, they will keep on rotating after collision with the same angular velocity. If they had no initial angular velocity, then even after the collision they won't have any angular velocity. That's the entire idea, provided the surfaces are smooth. So I'm assuming that the surfaces here are smooth. So if the surfaces are smooth, that means I ignore friction, no friction tangential to the contact surface, because a tangential force of friction here will give rise to a torque. We don't want the torques. So if the surfaces are smooth, that is, there is no friction tangential to the contact surface, then omega or angular velocity of these objects will remain a constant. Angular velocities of these objects will remain constant. Then we have something called eccentric impact. So we had a central impact. The next thing that we have is called an eccentric impact. And clearly this will be the case when one or both the centers of masses don't lie on this line. So if one or both the centers of masses do not lie on the line of impact. And how can that be? So maybe as an example I will show you a spherical object. So here is a small spherical ball that is being hit by some kind of oval object, maybe like this, and there is a contact surface here. So this green colored thing is the contact surface, and if I draw the line of impact, that orange colored line probably is the line of impact, and due to this object being asymmetric on either side of this line, maybe the center of mass is somewhere here. So this in fact, let me make that wine red brown dot. So this is the center of mass of this oval kind of object. oval oval shaped 3D object, and here this spherical object has got the center of mass on this orange line itself, so that's not a problem here. But now what happens is the force acting on this wine red oval object here will be acting through this orange line, will be acting along this orange line, and it will definitely create a torque about the center of mass, and this object is going to start rotating. Or maybe if it was already undergoing a rotation about its own axis, then it will either speed up or slow down. So there will be an angular acceleration alpha for this particular object. So keep in mind that in case of an eccentric impact, even if the surfaces are smooth, so no friction here, even then this force which is acting on one object during the impact is enough to give it an angular acceleration. So this is an eccentric impact. Then we have something called a head-on collision or a head-on impact. Head-on collision. So what is a head-on collision? Let's have a look at this impact itself, the central impact. Now when we have a central impact, there can be a case where the velocities of these objects are directed along the line of impact. So if velocities are directed or if initial velocities, let me say, if initial velocities of objects are directed along the line of impact, then it is a so-called head-on collision. So going by this figure which we have, let's take this example itself. Yeah, so here this orange line was the line of impact, and if the initial velocities of these objects, like for the green one, maybe the velocity was towards the left, v, and say v green, and for this one, the red one, probably the velocity was towards the right, so this is v red. And if the velocities are also along the line of impact, then what we have is a head-on collision. So in a head-on collision, we can make the assumption that it's in fact two particles that are interacting with each other. Again, I'm saying assumption because they are not exactly small objects, they are not exactly particles. That's because they will undergo deformations, and we will have to take into account those deformations also if we have to explain reasonably well all the things that are happening in the collision process. So we cannot really say that they are particles, but then we can still treat them like two interacting particles for the calculations of final velocities and final energies and so on. So in case of a head-on collision, you will have to ensure that the velocities Vr and Vg are directed along the line of impact, and that also helps us to define what is an oblique collision. So when we have an oblique collision, the velocities may not be directed along the line of impact. So if I just take this figure, so you have this red ball which is undergoing a collision with the green ball, let us say, and if I draw the line of impact, probably I'll draw a line like this in this case, and the center of mass of this red ball is at its geometric center there, and for the green ball is at the geometric center here. And maybe before the collision, the red ball was traveling this way, velocity of red, and the green ball was traveling in some other way, perhaps like this. So maybe a bit more inclined, so maybe like this, velocity of green. Maybe these are the velocities. So you still have a central impact. You still have a central impact because the centers of masses of both these objects are still lying on the line of impact, but it is no longer head-on. It is going to be an oblique collision, and in this oblique collision, still the objects will not have any angular acceleration, because the forces that are acting on one and on the other because of each other, these forces will still be going through their centers of masses, so no net torque about the object, about the center of mass. But then the final velocities will be in different directions to their actual velocities. So here, at least in case of a head-on collision, for the red ball as well as for the green ball, the final velocities will be directed along that orange line itself. But here in this case, the final velocity of the red ball will be in some other direction, and for the green ball will be in some other direction. Perhaps if I show you the directions using this wine red arrow, probably like that and maybe like this. And by how much do they change? It depends on their original velocities and their masses and all such things. So please keep in mind that we have all these things. Now first, we will start off with an analysis of one-dimensional head-on collision. Head-on collisions can be said to be one-dimensional all the time. So everything will happen along the line of impact. So we will start with a head-on collision, one-dimensional collision. Then we will go on to an oblique collision.